Hello, this is Dr. Viv. I would like to discuss a procedure called the Gram-Schmidt orthonormalization procedure. So suppose you're given a set of n vectors which are linearly independent. Let's recall what that means. It means that if I have real numbers which are non-zero and I set the formal linear combination of these vectors equal to the zero vector, then the only solution to this equation is that each of the AIs are equal to zero. In other words, the only way that the n vectors can depend on each other is if these coefficients are exactly zero, which means that you cannot write any of these vectors as a linear combination of the rest of them. So that's what the linear independence means. So you have n vectors which are not exactly they don't have any relationship between them except that they are linearly independent. Can you create a basis that contains only orthonormal vectors? Orthonormality means that they are not only orthogonal to each other, that is making a 90 degrees, but they also have a unit length. So there's a set procedure for this, and the procedure starts as follows. You start with one of them, any one, pick x1 for example, and you can certainly orthonormalize that. So let's form this vector e1 hat is equal to x1 divided by the magnitude of x1. The norm of x1 is denoted by this double bracket. So in practice, when you want to find the norm of x1, what you do is you take the dot product of x1 itself and take the square root. So I'll get x1 dot x1 and then the square root, and that'll be the norm of that vector. So that gives you the first vector. How do you find the rest? Well, to find the next vector, let's form this vector known as zeta 2, and zeta 2 is defined to be x2 minus the component of x2 in the direction of e1, like that. So if I subtract from x2 the component that is in the direction of e1, I'll be getting a vector that's not in the direction of e1. So this vector will then be our basis or the seed for our next element, e2, and that e2 is just zeta 2 divided by the magnitude of zeta 2. And by construction, e1 dot e2 is exactly 0. Now, we can proceed like this for all the remaining ones. Each time you subtract more and more components. So for example, the ith element, zeta I, is going to be xi, and then from that xi you subtract the component in the direction of e1, and then you subtract the component in the direction of e2, and you keep doing that all the way up to the I minus 1th component. So this way they're completely orthogonal to all the previous ones, and then you can get the new ei by the same process of taking zeta I and dividing it by its norm. So this is the Gram-Schmidt orthonormal procedure, and it gives us the final orthonormal basis. Now it's best illustrated with an example because this is pretty abstract. So what I'll do is, the previous problem we actually had a eigenvalue problem that gave rise to two eigenvectors corresponding to the two eigenvalues. That would be the video MM17. So if you want, you can go look at MM17 for the example. So what I'll do is I'll write those vectors x1. I'll write them as x1 equals 1 over root 2 1 1. Well, as a matter of fact, you know what I'm going to do? I'm going to just think of this as 1 1, and the other vector x2 will be equal to 2 comma 1. Let's not put any normalization signs in front of them yet, because this orthonormal procedure will actually take care of those things. So I'll remove this. In the earlier problem, we normalized each one of these vectors. So let's take these vectors to be unnormalized. So I'll put x1 arrow equals 1, 1, and x2 is equal to 2, 1. Now let's form E1 first. E1 is the vector x1 divided by the magnitude of x1. Well, that's the prescription I'm following. So, and that's just going to be 1, 1. And the magnitude is going to be root 2. So that's 1 over root 2. That's as you expect. And if you want to write it in terms of I hat and j hat, you can write it as 1 over root 2 I hat plus j hat. That's another way of writing this if you want to go to the vector space R2. What about zeta 2? There are only two vectors, so there's only going to be E1 and E2. Now to form E2, the intermediate stage is to form first what's called zeta 2, just like we formed these zetas first. So zeta 2 is going to be x2 minus the component in the direction of x1 of x2. Well, let's find out what that is. Now I'm going to save space. To save space, I'm going to write these as row vectors instead of column vectors. So it's going to be 2 comma 1 minus, well, the dot product is going to be 2 comma 1 dotted with 1 over root 2, 1 comma 1 in the direction of E1, and E1 is going to be that, written in terms of row vectors. So that's the computation. Let's proceed to do this. That's 2 comma 1. If I take the dot product, I'll be multiplying the x components and the y components and adding them. So that's going to be the 1 over root 2 and the 1 over root 2 become 1 half times 2 times 1 plus 1 times 1, all in the direction of 1 comma 1. Let's proceed to find what this is. So that's 2 comma 1 minus, well, that's 3 halves, 1 comma 1. Well, that's not too difficult to do. Multiplying 3 halves inside, I get this. And so our vector zeta is just half comma minus half. Now the last step is to find the magnitude of this zeta 2. Well, that's going to be by the Pythagorean theorem, square root of 1 half squared plus negative 1 half squared, and that's going to be a quarter plus quarter, which is again 1 half, so that's just 1 over root 2. And finally we can set up our E2 vector. E2 unit vector is the vector zeta 2 divided by the absolute value, or the norm of zeta 2. So that's going to be 1 over root 2 of half, actually it's 1 divided by 1 over root 2, so I should be careful here, half comma minus half. So that's going to be root 2 times, well, root 2 divided by 2 times 1 comma minus 1, or in other words, it's 1 over root 2, 1 and minus 1, written in the column vector notation again. Let's geometrically see what's going on here. I would like to show some interesting features which can be observed if you look at the geometry of this entire process. Let's go to the two-dimensional plane. Fortunately, these vectors are in the first and the fourth quadrant, so I don't have to draw the remaining R2. So this is the x-axis and that's the y-axis. Let's draw the vectors x1 and x2 first. x1 is going to be 1 comma 1, x component is 1, y component is 1, that's going to be your vector x1. Vector x2 has got x component 2, y component 1. So you can clearly see they are linearly independent, but they are not orthonormal. They make some acute angle between them. So what have I done in getting E1? It's the same as 1, 1, but it's divided by root 2. So that vector is going to be a smaller vector. Because 1 over root 2 is 0.71, so it's going to be a smaller vector. Okay. Now from let's find out what this is. I have taken x2 dotted with E1. x2 dotted with E1 merely refers to the component of x2 in the direction of E1 times E1. So that will be this vector, which I'm writing with a, let me try green, with a green arrow. Green arrow refers to the vector x2 dotted with E1 in the direction of E1. Now, if I take this x2 vector and subtract from it that one, what will I get? Remember vector subtraction, it is this vector that you'll get. So that's zeta 2. Because remember, in vector addition, zeta 2 plus x2 dot E1 is equal to x2. You go from the tail of this to the head of that, then from the head of that, tail of that one to the head of this one, and that's the same as going from the tail of the first vector all the way to the head of the second vector. That's what vector addition is. Now if I subtract both sides by this term, then I get my construction for zeta 2. Okay, so that makes complete sense. Now last step is to take the zeta 2 vector, which is this one here, and divide it by the magnitude of zeta 2. The magnitude of zeta 2 is small. You can see that from the figure itself. It's smaller than, for example, E1. In fact, it is 0.7. If I now divide by 0.7, I'm going to multiply the whole thing by root 2, so it's going to be a longer vector than that. And I'll put that vector in the origin. So it's parallel to this, but longer, and that's E2. So you can clearly see that E1 and E2 make a 90-degree angle, and we have achieved our aim at creating an orthonormal basis. Now I have to warn you that this Gram-Schmidt procedure does not respect the original eigenvalue problem, because these two were the eigenvectors of the eigenvalue problem. They were the span of that eigenvalue problem. So the spans are not preserved. In other words, I cannot claim that E1 is still an eigenvector in the with the same eigenvalue, but E2 is not. So E2 will not be a eigenvector of that previous matrix A. So that's one of the important things to think about in this procedure. The Gram-Schmidt process does not preserve the spans for the eigenvalue problem, for the original eigenvalue problem. But the vectors at the end are certainly 90 degrees to each other. Later on in the course, we'll be studying the same Gram-Schmidt process, but for infinite dimensional spaces involving functions rather than vectors. But this will be a first pass at the Gram-Schmidt process before we come to that more complicated procedure.